These are your plate tectonics flipped notes. The first thing is seafloor spreading. Seafloor spreading is a theory that says that the crust in the upper mantle, that's the lithosphere, that's the hard part of the earth, they float on the mantle, the liquid part, the mushy-gushy asthenosphere. So lithosphere is the hard part, asthenosphere is the mushy-gushy mantle. You can see in this picture that the upper crust and the upper mantle are hard. They're very thin compared to the mantle, the red portion of this picture. You can see the blue arrows. Hot magma is rising to the surface. It's being heated by that outer core. The cooler magma, being cooled down by the crust, is actually being pushed down into the mantle, which this is called a convection current. So you can see that there's a circulation there. It's actually pushing, driving those plates around the world. This is a picture of the world and the plates that are found on it. They're kind of like big rafts. They float on top of the asthenosphere. You can see that the North American plate, that's kind of that brownish color, has several borders with the Eurasian plate, the African plate, the South American plate, the Caucasus plate. We're going to do a little lab on this here in the next class period. Plate tectonics. How do we know this is true? It's supported by the fact that there are reptile fossils found on different continents, that if they were put back together, they would actually be in the same spot. Plant fossils, plants that wouldn't normally grow in that climate, that we have fossils of them in that climate, which tells us that the climate didn't change, it was the land area that moved. Rock structures. The Appalachian Mountain Range, our folded range that just runs right up that east coast, actually extends into Canada and then into part of Europe if you put these continents back together. And probably the most easy to identify one is the puzzle-like fit of the continents. When all the plates fit together, they make this super landmass called Pangaea. So this is Pangaea while it was moving. The upper left-hand corner, you see it all put together, and then in the bottom, you can see where we are today, and you can still see how these continents would fit together like a puzzle if we were to take out the ocean and put it back in. Seafloor spreading. This is what's driving, pushing us apart from South America and Africa. It's hot, molten material, this magma, under the earth that is forced to the surface at the divergent boundaries. The oldest rocks on this are on the outside of the ridge, and the youngest rocks are next to the ridge. The magnetism of the rock changes on both sides of the ridge at the same rate, and the divergent boundary, where the boundaries between two plates are moving apart, actually makes this mid-Atlantic ridge. So divergent boundary, moving apart, it's a tension force making the mid-Atlantic ridge. That's an important one. So this is an example of the mid-ocean ridge. You can see here that the green bars represent magnetic fields, so the reversal. So you can see that there's the same pattern on either side of that red asthenosphere that's coming up through. That's the magma. The oldest rocks would be on the outside of those green bands, and the youngest rocks would be right next to that red. Those are the newest rocks being made. So in this picture, you can see that there's an orange stripe right down the middle. That would represent new land being formed. The blue and purple on the outside would represent old land being formed. This is the picture of this divergent boundary we're talking about. You can see right here the arrows are actually pushing apart, that tension force. And you can see everything is pretty much underneath the ocean except for one piece of land, and that's Iceland. Iceland is the only above water surface on that mid-ocean ridge. So it's very well studied. It's a volcanic island, and it's actually growing just like our ocean is growing. So we have some collisions. These are convergent boundaries, when the boundaries of two plates are actually moving together. We've got ocean to continent collision, we've got ocean to ocean collision, and we've got collisions of two continents. The first picture is an ocean to continent collision. B, the second picture, is going to be an ocean-to-ocean collision. And then the last picture, C, is actually continent-to-continent collision. And you can see there's those folded mountains that we've been talking about. So the subduction zone is where a more dense plate will sink under a less dense plate. This is going to cause a trench, a very steep, deep-sided depression in the ocean floor, and it's going to cause volcanoes. This is going to be the ocean to continent collision. So here you can see that one plate is actually being forced under. Where it's forced under, you can see that there's a dip, there's a trench there. And also where it's forced under, you can see that there's earthquakes occurring. But as that mantle, or that crust gets pushed down, it's going to melt and it's going to come right back up, right off the coast in what's called a volcanic island arc, or volcanoes on our continent. Ocean-to-ocean collisions are a little bit different. Both plates bend downward because neither is more dense than the other one. This is going to cause a trench. So you can see here that these two plates, both of them are going to dip down, and you're going to get an ocean trench. The Marianas Trench is going to be formed like this, deepest trench that we know of. Continent-continent collisions are going to make the plates buckle and fold to form mountains, just like those folded mountains that we've been talking about. The transform fault boundary. This is one plate boundary that slide past each other. This is going to cause earthquakes. This is that shear force we talked about with earthquakes. So here's a picture of the plates and what they're doing. So you can see right up along the west coast of the United States, we've got a plate boundary. Between United States and Africa, we've got the mid-ocean ridge. That's a divergent boundary. And then over along Japan and China, we've got some convergent boundaries going on. This is a transform fault, and we've talked about that shear. We've talked about the San Andreas Fault. This picture is of California, that San Andreas Fault that we've talked so much about. The North American plate is actually moving south, while the relative motion of the Pacific plate is moving north. So will it fall off into the ocean? No, but it will stick out there one day.